Alright, I'm going to talk about LoRA. It was actually a little bit ago that came out in 2021, but has kind of recently been used for large language models and fine-tuning them. I was actually under the impression with Alpaca LoRA that this is actually a compression algorithm, but it's not a compression algorithm. It's used for fine-tuning, but with a small number of parameters and with a small number of parameters. So, so let's just go through it. So if I have a model, let's say I have this input, whatever that may be, and then I have some layer. So this will be our input X. I have some layer L, and then I have some output Y, some transformation. Then a common way to fine-tune this is to take this output, whatever this may be, and then directly take the loss of this in terms of the objective you want. So say we had this model. Actually, I'm going to call this M. So this is our entire model instead of just one layer. And say we want to fine-tune it on some tasks such as translation. Say we have a BERT model or a GPT model, and we want to fine-tune this so that it's very good at translation from, say, English to Spanish. Spanish. Then like an easy way to do this is to just take this loss and backpropagate through the network like normal. And the idea is that it will be a lot easier to fine-tune because it already has knowledge of Spanish and how language works, so it'll be easier and faster to fine-tune. And that's why you would do that. And also, since it has some more knowledge of the world it is looking at, it may do better on the downstream task. But there are two problems with this. The first one being, this takes up a ton of space in your memory. The amount of memory it requires is as big as the model. You have to retrain every layer in the model, and that's just not. If you have a small computer, that's not going to be too easy, especially if it's a massive model like GPT or BERT. A second problem with this is you don't have, once you fine-tune it, you don't have the original model. So this model is just whatever the fine-tuned version is, and you can't get the original model back from there, which is quite annoying if you want to take the original model and then fine-tune it again. And you have to save all these weights again, so it's very cumbersome to do this. Now if I go back to the layer example, instead of the whole model, we'll just look at one layer. Then what you can do is you can add some adapter module. And we'll make this blue. Ooh, frozen. So we freeze the layer. This layer was trained, let's say it was a BERT model. Then this layer was trained to do some task, some masked task in BERT. This layer knows about language in some way. And what you can do instead is keep that layer frozen, put the output also through an adapter module, and just train this adapter module. And this way the adapter module learns how to kind of edit the network and find out, kind of change how the network hidden layers go through the network so that it's better at translation. And you can make A small, which will reduce the number of parameters that you need to train. And you can also you can think of it as like a plugin to something. Like we have this base model, BERT, in our example, that is frozen, and you can think of training this plugin. Maybe that is to do a translation task. You just throw this adapter as your plugin into the model, and then you can take it out to do the original task, which is whatever you want BERT to do. But you can throw the adapter modules into the network, and then it'll be good at your task. So you kind of have both parts to the model. It's both good at the original task that it was trained to do. For BERT, that would be masked language or masked token prediction. But then whenever you add the adapter, it's also good. It's good at the translation task. So now you have both. And it's easy to get the original model back. What LoRA does is it takes this adapter module and it makes it really small. In this case, they work with linear layers. So I have this X here. X, where X is in R sub D, or RD, where D is whatever size that vector is. If this was 3, then it would just be if D was 3, then it would just be a 3-part vector. And you have this weight matrix, W, which is in R of D by D. In our case, it'll be D by D, but it can be D by whatever. And this is our normal output. Then you have a Y, which will be in the space RD. And this is the normal network, whatever your linear layer may be. For example, in attention, you have multiple linear layers. You have the query layer, or your query weight, your key weight, and your value weight, W sub V. And then you take your input, you put it through these weight layers, you compute and this gives you the query keys and values. Then you compute your query key matrix. I'm going real quick through attention, just because I'm going to assume you already know how attention works. If not, have a video on that. And I'm going to highlight the weights in red. So you compute your query key matrix. That's not a weight. It's not a linear layer. It's just multiplication. You multiply that with the values, and now you have your output. And then you send your output through another linear layer, which we'll call L. And then you have your hidden output. In attention, you have 4 hidden layers, specifically. So you can apply this to you can apply LoRA to 4 hidden layers. And this is just a more zoomed in version of the linear layer. Our normal path will be you take this X, you put it through this weight matrix or linear layer, and then you get an output. And that'll be your normal BERT weights or whatever that was trained on originally. What LoRA does is it freezes this, I'll highlight it in blue, and it adds 2 matrix multiplications, or two feed forward layers. This is A, which they initialize from a normal distribution with 0 and whatever the variance is, and then B, which is 0. That is just a 0 matrix. It's our in between. And the A matrix will be in R of D, or R D by R. Sorry. It's a D by R matrix where R is it's going to be some arbitrary value for now, and then B will be R by D. It'll be in this dimensional space. You can kind of see that by the bottleneck visualized here, where R is less than D. R is some arbitrary number. So if D is equal to 512, you can think of R as anything less than 512. For example, it can be like 2 or something like that. We'll go into what a good R looks like later. And this matrix multiplication here is the same, it results in the same output, the same shape output as here. So these will output, Y, I'll call this Y sub O, or Y sub O, and this will be Y sub N, old and new. And then you add these together. You add them together and you get your output, Y. And since this is initialized to 0, whenever you are initially fine-tuning this model, the weight matrix on the left, the original weight matrix, is the only thing having effect. And then as it learns, since this is initialized to 0, it initially has no effect on this sum, meaning that the network is just the same exact thing as it was before, just with some trash weights. But after one backward pass, this will no longer be 0 due to how backprop works. Since it's being multiplied by whatever these hidden states are, that'll be the gradient. And then it won't be 0 anymore, unless x is 0, but that's probably not going to happen. And you will and as you fine tune it, these layers will learn the downstream task, while this layer will stay in the original task. And to be more formal, if we have, it'll be y. If we have some layer, which is y is equal to wx, some linear layer, then the LoRA layer, this is our original, and this is our LoRA. Our LoRA layer will be, they show it down here, it is y is equal to wx plus ba, or abx, or bax. And our w is frozen, our ab is what we're training. And this is just basically 2 parallel linear layers that you add. And you can add this to any linear layer whatsoever, which is very nice. Now you may be thinking, why? Why would I do this? This is more parameters, right? Well, it's actually not more parameters. If let's take a look at an example. Let's say I have some weight matrix, which is 512. We'll show it like this. This is our weight matrix. It's 512 by 512. Our d will be equal to 512. D is equal to 512. So this will be a 512 by 512 matrix, our W, and this is our frozen matrix. That means our x is a vector of 512. That's our x. Goes through here, multiplied by 512, and you get your output y, which is also 512. Now, let's say we have our matrix. This will be our A matrix. Yeah, I'll just represent it like that. Why not? And actually, let me turn it over. This will be our A matrix, which we're multiplying by x, and this will be 1 by 512. I'm going to say r is equal to 1 because the math works out well, and also this is not a bad 1 is actually a really good r to pick because it's small, and it gives a good performance, which we'll show later. Now this hidden part right here between A will be a vector of shape. It'll be a 1. It'll be a 1 by 1. It'll be a 1. It'll just be a scalar at this point. This is our x, and I'll just say x sub h or whatever. And then you send this through the B matrix, B, which is, I guess it would be a long one. This is our B, and this is 512 by 1. And whenever you multiply it, you get an output of 512. So it goes into A, it turns into a vector of shape 1, which is just a scalar, and then you throw it through B, and it becomes a vector of shape 512 again, and then you add those together to get your output, just like we showed above and the equation. Now, if we're fine-tuning this, then we have to send everything through the weights, or the original weights, and the new weights. You can't get around not going through the weight matrix. Would be nice, but you have to send it through there, even though we're keeping it frozen. Because y is equal to wx plus abx, that means that the previous layer needs the information from w, and we can't get around not worrying about w. And that also means that the gradient of x also depends on w, or on the gradient of w. For example, if we have or if we had y is equal to it's wx plus abx, then our gradient of y or our derivative of y is equal to our derivative y of wx plus abx, dy over dx of that is equal to the derivative of wx plus the derivative of abx, which is equal to w plus ab, meaning that the derivative of x is dependent on both w and ab, meaning that all previous layers depend on whatever this gradient is, which depends on w. All this to say, we need the w gradient, which is a problem because we wanted less parameters. But if I show you how many parameters we need to store, then it starts to look better. In case of Atom stores 3 times the number of parameters. For Atom, we need to store x, we need to store, it was like the variance, and then the squared variances. And this is 3 different weights we need. So for every x value we have, we also have to store, or for every weight, sorry, I'll call that w. For every weight we have, we also have to store the variance of that weight and the squared variance of that weight. Meaning that for every one of these, we have to store that, when optimizing it, we have to store both the variance, or we have to store all 3, the weight itself, the variance, and the squared variances. So you basically have 3 times the number of parameters. But we're not fine-tuning w, we're actually fine-tuning a and b. And we don't even need to worry about the gradient of w. So let's go ahead and just write out what parameters we have to store when fine-tuning. In case of w, the number per params. So in case of w, we would have to store, the number of params we would have to store is 512 by 512. I don't know what that is, some massive number, if we're optimizing it. For A, we have to store 512, and for B, we have to store 512. And then we multiply all these by 3. But since we are not optimizing W, all you have to do is store 512 by 512, which is 1024. So if we were to optimize this model like normal, where we're just fine-tuning W, then you have to store 512 squared parameters, which is way bigger than 1024. And it's actually 3 times that due to Atom. So whenever you're optimizing, you store a lot less parameters with LoRA because of this R right here. And if you increase this R to 2, then it would be 1024, which is still a lot better than 512 squared. That's massive compared to 1024. So it's a very nice property. And that's one of the best reasons why you fine-tune with LoRA, why you fine-tune this A and B as opposed to this W. And there's 2 reasons. It's because of memory efficiency, as I showed down here, but also since you're storing a lot less parameters, the back propagation takes a lot less time, so it's a lot more efficient. And you can easily do this by like detaching this part from the optimizers, so not having the optimizer worry about this weight, so it doesn't have to store those values and with like PyTorch or something like that, whatever framework you're using. But just don't store the parameters of W and the gradients of W, and you'll be perfectly fine with the number of parameters you're actually fine-tuning. That's one of the nicest parts about LoRA. So you add this A, you have this adapter module that takes up very little space as opposed to other modules that exist. One nice part with LoRA is you can compress it. Remember that our function for LoRA is Wx plus AB, ABX. Now once A and B are trained, once A and B are fine-tuned, now you have this function here for everything, which is very annoying, meaning that for every linear layer we have, well, we actually have more parameters than if we were to just fine-tune W. That's a problem. But if you notice, both of these have x. You can pull x out, W plus AB, and now if I multiply, or if I add these two matrices together, remember W is in R of D by D, A is in R of D by little r, and B is in R of R by D. If you multiply these together, then your AB matrix is in R of D by D. Then we can add the weight matrices together, the new weights and the old weights, to have, let's say W sub n is equal to W plus AB. And that means Y is equal to W sub n x. And our W sub n is in R of D by D, which is the exact same shape as the original network. And this means that whenever you're storing this network, you have the exact same number of parameters as you would if you stored the original network. Meaning that you fine-tune this network, but you don't store any additional parameters. And so you kind of get the best of both worlds. You don't have to directly fine-tune W. You only have to fine-tune A and B, meaning that the fine-tuning is very small. The number of parameters you have to store in fine-tuning is very small. But the problem with past adapter modules is you would have to store that A and B, or whatever that may be, whatever that adapter part is, in memory as well, meaning that your module size was actually increased. But since you can compress it, that means that you don't store any additional parameters. So now you have the same shape as the original module. So it both has speed, less parameters when fine-tuning, and the same number of parameters when you're doing inference, which is it's the best properties you could pretty much have. In reality, you're probably going to store both W and A and B separately, or probably W sub n and then A and B separately. When you're inferencing, you'll only use this. That means that when you're doing inference, you only need to, the number of parameters you'll have will be the new W, which is the addition of A and B and W. And that's the same exact size as your network, but in your memory, in storage, in the cloud, wherever that may be, if you want to get the original W out of here, like let's just say I have my BERT model. This is our original. And then I have my fine-tuned BERT model, which will be F, which will be using W, and our fine-tuned version will be using W sub n, our new weights. Then I only have to store our new BERT module, but I also have to store the A and B weights. And if I subtract the A and B weights from this BERT module, or from the fine-tuned BERT module, then I get the original, since W sub n is equal to W plus AB. Then W is equal to W sub n minus AB. So if I store these two parameters, W sub n, which we're going to use for inference, this is used for inference, and I store the AB modules itself on the side, then I can get the original weights, which is a very nice property. And like I said, you can think of it like a plugin where you can just add it to the base model and remove it whenever you need to. So if you just subtract A and B, those weights, then you get the original BERT weights, or you get the original whatever model weights you initially had. So it's very nice, and very nice properties. Like all these properties are just so useful. The storage is efficient. You can compress it, or the storage is efficient, and the number of parameters that it results in is the same number as the original. So very nice properties. Just to conclude, now that we've gone over BERT, I just want to show some of the results. So if we look at LoRA on the left, then you can see if we look at the bottom, this LoRA part, then on a lot of the tasks, a lot of the downstream tasks, which is probably like translation or stuff like that, They actually use BERT. Yeah, they use Roberta in their case. So BERT. If you take those linear layers and the attention in BERT and add LoRA to them, then on downstream tasks it actually does better than some of the other fine-tuning strategies, and pretty comparable to in some of the other tasks, but for most of them it just outperforms the rest. So it does a pretty good job compared to. So it's both small, it's easy to store, and when doing inference you don't have to add any new parameters, but it also does better than some models. So you got even more of an advantage for using LoRA. And finally, I want to show the R usage. If we look down here, then you'll see that an R of 1 is really good. Look at the R of 64 compared to an R of 1. The difference is not very massive. And this is validation accuracy on some downstream tasks. You can see that using an R of 1 is it's pretty reasonable. Let's just say we don't use an R of 1. If we use an R of 2, that's basically the same as using an R of 64. And if we use an R of 4, that's even better than using an R of 64. So if we just say R equals 4 is our base, then you're storing way less parameters. Remember, our original W was 512 by 512. But what you would be storing if you used an R of 4 is 512. It's 2 times 512 times 4, which is equal to 512 by 8, which is much less than 512 squared. And you get a really good performance with that. So that's pretty much LoRA. It's pretty simple. You're just adding these extra weight matrices to that you're fine-tuning instead of fine-tuning the original weights, and then you can store them efficiently. And it's very powerful. So that is LoRA.